We can continue our exploration of these functions by proceeding as if the Taylor series are like long polynomials. Hence, computing things like integrals or derivatives can be done term by term. Let's consider what the derivative of the hyperbolic sine of x would be. Well, we can differentiate the terms of the Taylor series. Since the derivative of x to the 2k plus 1 equals 2k plus 1 times x to the 2k, we can see by dividing by 2k plus 1 quantity factorial and summing as k goes from 0 to infinity, that the derivative is the sum, k goes from 0 to infinity, of x to the 2k over 2k quantity factorial. That is simply the hyperbolic cosine of x. In similarity to what happens with trig functions, the derivative of sinh is cosh. Likewise, what is the derivative of cosh of x? If we differentiate term by term, we can see that the derivative of x to the 2k is 2k times x to the 2k minus 1. Now we have to perform a shift in the index here in order to avoid problems with what happens when k equals 0. Reindexing properly gives us the sum, k goes from 0 to infinity, of x to the 2k plus 1 over 2k plus 1 quantity factorial. That is the hyperbolic sine of x. And so we see that the hyperbolic trig functions are very nice. The derivative of sinh is cosh. The derivative of cosh is sinh. And this becomes clear from the Taylor series. Now, we're used to writing out the Taylor series term by term. Of course, since there are infinitely many, we can't write them all. We typically use a plus dot 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 or an ellipsis to connote what happens in the tail of the series. But there's another terminology that we will begin using, that of HOT, or higher order terms. This is an informal way of saying etc., and it can be a bit helpful. For example, you might say that cosine of x is 1 minus x squared over 2 plus higher order terms. We could say that sine of x is x plus higher order terms, or x minus x cubed over 3 factorial plus HOT. We could stop whenever we feel like. That's a convenient thing to do when performing computations on Taylor series. We'll use a more formal bookkeeping mechanism soon. Let's look at this in the context of a simple example. 1 minus 2x times e to the sine of x squared. We'll begin with the Taylor series for sine of x squared, which is simply x squared minus x to the 6th over 6 plus higher order terms. What happens when we exponentiate this? We use the Taylor series for e to the x. 1 plus our quantity above plus 1/2 times that quantity squared plus 1/6 times that quantity cubed, etc. Notice that I'm using plus higher order terms liberally in order to ignore things that aren't going to matter for the first few terms. To simplify this, we go degree by degree. The constant term is 1. There's only one quadratic term, namely x squared. Are there any fourth order terms? Well, yes, there is. 1/2 times x to the 4th. In the 6th degree terms, there are 2 of them, but notice that the coefficients balance each other out. And so the coefficient of the 6th order term is 0. We are left with a Taylor series of 1 plus x squared plus x to the 4th over 2 plus higher order terms. Now, to get the Taylor series for our original function f, we simply take 1 and subtract 2x times the quantity obtained above. I'll let you show, with a little simplification, that this is 1 minus 2x minus 2x cubed minus x to the 5th plus higher order terms. If you want more terms, you can get them. It will take more work.
We've now learned not only what Taylor series are, but how to compute them quickly and cleanly. Along the way, we've been introduced to two new characters in our story, the hyperbolic sine and cosine. In our next lesson, we're going to consider what happens when things don't work out so well. We'll deal with issues of convergence.